Next up is shear stress. Shear stress is the stress as experience where we are shown at the same each point located on the section. Basically, here, if you're checking out this particular figure, we have 4 points of contacts A, B, and C. There's an applied load here, and the shear stress is being experienced at this particular surface. So when there's applied load here and there's two surfaces here, the meaning it's double shear. Normally with single planes, you would only experience one single shear force here. Okay, so per one applied force here in this particular cross section, there's two shear force being experienced, and we're looking at the what we're looking at here is getting the V to get the average shear stress theta. Okay, so V here is the internal resultant shear force on the section determined from the equations of equilibrium. So normally this goes F is equals to 2V, and normally you're looking for V here, you will get first the F. So you just have to divide that applied force by 2, since there's, two shear force theta. And of course, the area of the cross section usually is provided naman rin. This one is pure shear, and there's a lot of math here. And luckily, we won't be needing this. In other words, all four shear stresses here must have an equal magnitude and must be directed either toward or away from each other at opposite edges of the element. So yeah, there we go. So yun yung shear stress dito when it is being experienced. I also added the procedure for analysis here. So first things first is you have to identify the internal shear, meaning you have to draw the necessary free body diagram, the internal loads, in order to calculate for force V, or the shear force. Then after that, you can all start, you start solving for your average shear stress, which is tau, for example, represented by the Greek symbol tau here. It equals to shear force divided by um, area sheared. Okay, so let's try for several sample problems so that we understand what the average shear stress is. So here we have a figure here, and we need to determine the average shear stress in the 20 millimeter diameter pin at point A and the 30 millimeter pin at B that supports the beam below. So here, so this is the another view of it. This is like top view. Okay, so we are here to record the to determine the average shear stress at pin at point A and pin at point B. So this one in particular. Then after which we here to first build our FPD, since this is a pin, so we have reactions here. We have X and Y reactions here. This is a cable, so we have let's just label this as force FPC, and we will build the FPD to determine the internal loads, and the internal load is just like so. There we go. Let's hope our assumptions is correct. And then after that, we now establish our equation of equilibrium to solve our unknown loads. So in this particular case, even if you didn't moment at point A at first, you would have to do that in order to solve the unknowns dito. But what I did was I created the equations summation of forces across x-axis and then y-axis. As you can see here, it's pretty problematic since FPC is unknown, AX is unknown, AY is unknown, FBC. So my only choice here is to really moment at point A. So that's gonna be negative 30 times 2 meters plus FPC times 4 over 5 um, times 6 kilonewton meter, and we will have FBC is equals to 12.5 kilonewton. And from there, we can get AY and AX respectively. So AY here is going to be 20 kilonewtons, and then AX here is going to be 7.5 newtons. There we go. And then from here, I need to know the area sheared. So in this particular case, AY, AX. So these are components of force A to be exactly. So we need to find its magnitude first. So we get that by using the Pythagorean theorem, square root of AX squared plus AY squared. So F of A here is 29.36 kilonewtons. So that is our shear force here. And there we go. that will be our force pala there. So that's not the shear force. To determine the shear force here, we have to look at it. We have to look at the pin again. Okay, we have to look at the pin again. So again, so this is just the force FA here. So to determine the shear force here, we have to look at the pin again and create this particular FPD. So as you can see here, area sheared is being shear. It's experiencing double shear. This is the applied load. This is the beam, and this is the area being sheared. So those at that particular cross section, it is experiencing shear force here and then another shear force here. So hence the equation FA equals to minus 2 VA, where VA is FA over by 2. So our shear force here is 10.68 kilonewtons. So again, do not be confused with this particular force and this one. Okay? So next up here, we can now solve for shear stress. Average shear stress is just simply 10.68 divided by pi over 4, 20 millimeters squared, 20 squared millimeter squared. That will give you around 2.76 megapascal. So we can do the same way here. It just so happened this one is experiencing single shearing only, this particular area. So no need for this particular equation. It's not experiencing double shear at the moment. So for tau B, FBC here is simply equal to our shear force, which is 12.5 kilonewtons. And then from there, we just substitute it, and we will have the average shear stress at point B at 17.68 megapascals. Okay. We have another sample problem, and then I think this is one of your exams, I think. I'm not sure. But I think it's a good way to practice our double shearing. At least here, it is stated here that the all pins are experiencing double shear here. Okay, so here we are needed to determine the maximum magnitude P of the load. Uh, P of the load the beam will support if the average shear stress in each pin is not allowed to exceed 60 megapascals. All pins are subjected to double shear shown, and each diameter of the pin is 18 millimeters. So here's another one, but that's completely reverse. So instead na hinahanap natin yung shear stress, we're here to determine yung maximum allowable load dito. Um, the equation should be pretty much the same, but the equations should be laid out perfectly algebraically naman. Eh. So here we are given this one. Our allowable stress, shear stress, is 60 megapascals. Our diameter of the pin is 18 millimeter, and we're here to record what is the maximum P or maximum load. We first things first is we determine the FBD, so we can just determine this particular section here. So that's gonna be something like this one. So we have FBC, we have a pin here, AX and AY, then P, and then 30 degrees. And then from there, we establish our equations of equilibrium by getting the summation of forces at X, Y, and then of course moment at this particular point. So we start with the moment at point A to eliminate AX and AY to determine what FBC and P is all about. And from here, we can now set up the equation of those, and eventually it will be written as this. Simplifying further, this sine 30 degrees and 6 is going to be just 3. Simplifying further the equations, FBC is going to be like this, and the FBC is equals to 2P. So that will be our first equation there. Next up, summation of forces for X. So that's going to be AX minus FBC cosine 30 degrees, which will give us AX is equals to 2P squared of 3 over 2. Eventually, that's AX 1.7321P. That's our equation 2. And then for FY, AY would be simply, there we go, that would be AY equals to 2P. AY will become P, yeah. So my negative 2P plus P will be P. There we go. So at this point, we can now determine the load at FA. So to find the total load here, it's just simply that just like we did earlier, it's going to be just a square root of square root of AX squared plus AY squared, which gives us 2P if you just substitute it algebraically lang. So we have AX here, And you're gonna be surprised it's gonna be 2p anyway. Okay, you can solve it naman. And then finally, our FA here is now equal to FBC, which is technically equals to 2p. There we go, as stated here. You know, and then from here, the pin's a double shear. So if we're gonna look at it again, it's gonna be to determine the shear force. That's gonna be F minus 2V equals to 0, where V is equals to F over 2 equals to in this particular manner. And F here is our F here is FA and FPC, which is equal to 2P. It's going to be 2P, so our shear force here will be equivalent to P. Now that we determine our shear force P, we can now just reverse it. So recall our equation. Tau is equals to P over A. We're here to determine maximum P. So P here will be equal to tau times area. So that's going to be 60 Newton per millimeter squared. That's our allowable shear stress times the area, which is pi over 418 squared millimeters squared. And this will give us 15,268 newtons, or simply put 15.27 kilonewtons. And that's about it.